So hi, my name is Rita, and I'll be talking about unclonable, non-interactive zero knowledge. And this is joint work with Dr. Takarana. So just like to introduce you to this area of unclonable cryptography, the main motivation is basically the no cloning theorem, which is a fundamental theorem in quantum computing, which is to say that you cannot create an independent and identical clone of an arbitrary unknown quantum state. So what this means is that, so of course, if I knew the quantum state, then I can create a clone of this. But the whole goal of this theorem is basically saying that, and of course, you can also create states that are entangled, if you're familiar with the concept of entanglement. But this no cloning theorem is to say that as long as the state is unknown, then you can't create a separate unentangled copy of the state. So this has basically led to a lot of unclonable primitives, including some primitives on quantum money, as well as some primitives in unclonable encryption. And there's going to be some nice talks that'll be happening after this, as well as later in the day, I think, on quantum, on unclonable secret sharing. And so there's a lot of very nice work in this area. And the motivation for this particular work was that there's an open problem that was posed in this literature that asked the question of, can you construct unclonable quantum proofs? So previously in the literature, we had talked about unclonable encryption schemes, but no one had really looked at unclonable proof systems. And then the question that was also asked was, do these proofs relate to quantum money? So just to give a sense of like, what in this work, we construct unclonable proofs, and these actually have applications to signature schemes and credentials. So you can create unclonable signatures of knowledge, as well as credentials, which are revocable, and as well as unclonable versions of these anonymous credentials. And another application of this is to actually get certified deletion for NISIC proofs. So this is just to summarize like some of the applications. If you have any interest in these applications, you can see the full paper, but just to give a sense of what these signatures might be useful for. So you might ask like, what is the point of having an unclonable signature scheme? So one of the things that you can think of, a use case, an application, is to say that, well, you can non-interactively prevent replay attacks. So now what is a replay attack? A replay attack is when a sender is sending some kind of signature to a receiver, and the signature is typically in the context of being a way to authenticate this sender. And so an adversary who's passively listening in on this channel could observe this signature, and since the signature is classical and copyable as a result, the adversary who's listening in could actually copy this information, and then at a later time, send this signature to the receiver and have them authenticate them as the original sender. So this is a big problem in security, is this problem of replay attacks. And currently, the approaches that we have towards solving this is that the sender and receiver have to first have an interactive kind of protocol in which the receiver will send some type of one-time token, like a session ID, to the sender, and then the sender will sign their message along with this token. And so this kind of unclonability-based approach would be to say that the sender, without having to have prior communication with the receiver, could just send an unclonable signature of the message that they want to have signed. And so in particular, just to give a sense of what this may, where this may show up, it actually will show up in, so this I mentioned before, and sorry, this goes backwards, in a previous slide about unclonable signatures of knowledge. So signatures of knowledge and these NISIC proofs, they help because then you can have anonymous signatures. You don't have to have rounds of interaction to actually set up this token and then have a signature. You can just send a signature with regards to you don't even need a public key to respond, or a public key or symmetric key, specifically a public key to set up in order to send the signature. Okay, so But we're not really focusing on the application. What I will focus on is focus on this, the NIZC itself, the unclonable NIZC. So firstly, just to recall, the definition of a non-interactive proof system, specifically for NP, is we'll be working in the setting where the prover and verifier have some trusted setup, which we call a common reference string. And the prover will send a single message over to the verifier. And then the verifier will output accept or reject. And we say that this proof system is complete if the prover only accepts true, if the statement is true, the prover will always accept. And we say that if the statement is false, the proof will be sound if the verifier accepts with only negligible probability. And so then now we actually talk about this additional property, which is the property of zero knowledge. And to leave aside all the technical definitions, which are very in-depth, we'll just say that on a high level that a verifier, a malicious verifier that's trying to learn information, extra information, cannot learn anything other than that the statement is in the NP language. So, okay, so now I'm just going to introduce this problem. So previously in the literature, there was no definition for unclonable proofs. So the first problem is, of course, to actually define this. So when we try to define a prover sending a unclonable proof, the definition of unclonability we're going to talk about is that, say that the prover and the adversary, the prover sends the adversary a proof. And then this adversary can then somehow do some computation offline. And if this adversary is then able to turn around and prove to two different verifiers the same, using the one proof that it received, is able to convince two different verifiers, then they've broken unclonability. Then they've essentially somehow captured this notion of cloning the proof. So we want to specifically prevent this type of attack. So now that we're, now just to give some kind of intuition of what the difficulties are when we try to actually define unclonable proofs. So the first thing is that it must be quantum, because you'll notice that if the prover sends a proof to the adversary, and if the proof is itself just classical, purely classical, the adversary can of course clone this and then send both two different copies to the two verifiers and have them accept. So now we know that this unclonable proof must be quantum. So then I will also argue that it must have some zero knowledge, flavor of zero knowledge, because say that the prover just sends the witness in the clear to the verifier. If this is the case, then the verifier can of course just learn the witness from this proof and then use this classical witness, because again, we're talking about NP, can use this classical witness and just produce two proofs and generate honest proofs and send to two different verifiers. So now we know that this proof must also have some kind of notion of zero knowledge. And I'll further argue that to be interesting, it must also have a notion of non-malleability. So this definitely, of course, has to be defined a little bit carefully, but I'll just give you the sense that if the prover had a proof for a particular instance X, and then the adversary shouldn't be able to learn enough information such that the adversary can produce two proofs for some different instance, for some different instance, and have the verifiers both accept. And this will be like this version of non-malleability is it's what so in the literature this was previously studied under something called simulation soundness. But this is just if you're interested, you can look up simulation soundness or simulation extractability and see like more technical definitions. But intuitively, we don't want the adversary to receive a proof that it learns more about than it knew before. And so it can only pass on the one proof it received. Okay, so now that we've discussed a bit of the definition, we actually talk about how to construct the unclonable NIZC. So we do this both in two different models. One is in the common reference string model, and the other is in the quantum random oracle model. And so the first one is that if you assume public key quantum money, public key encryption, and commitments, as well as a simulation sound NIZC for NP, then you can construct unclonable NIZC in the common reference model. So these, in particular, the public key quantum money, I will explain in a minute. And I also want to mention that the protocol also works in the quantum random oracle model. And this only needs, besides quantum money, you just need a Sigma protocol for NP. And so, yeah, so but I'll talk about the CRS model one. So now, in case you already know, or in case you want to learn a little bit more about public key quantum money, public key quantum money is basically a protocol in which there is some kind of centralized, I mean, in the example I'm giving, there's a centralized bank, and the bank issues quantum banknotes. And these quantum banknotes have a classical serial number. And so this, I've just denoted this as like having this ket notation for the $ as being the quantum part of the quantum banknote, and the S as being the serial number, the classical serial number. And so yeah, the quantum money scheme is basically the public key part is that if the bank issues these quantum banknotes, then anyone can verify that this is a valid banknote. You can imagine just something more similar to the idea of issuing banknotes, like our classical banknotes that we have like in our wallet now, except imagine a quantum version where the banknote itself has some quantum state embedded in it. So now this quantum money, basically the main important property that we use is this property of unforgeability, which is to say that if the bank issues a banknote to perhaps some adversary, the adversary cannot offline basically figure out a way to construct two different banknotes such that the quantum states may be different, they're allowed to be different, but the serial number is the same. And so it should not be possible for this for any adversary that receives a quantum money banknote to forge it, basically forge based on the classical serial number. So in particular, this just intuitively, what this kind of means is that our no cloning theorem had said to us that the quantum state, because I don't have any information or knowledge of the quantum state, it is in some sense unclonable. And now that there is this classical serial number tied to this quantum state, you can basically imagine that this sort of unclonability property is transferred to this classical serial number. And this is like the key takeaway really in terms of quantum money. The power of quantum money and using it in protocols is that, yeah, you have this somewhat unclonable quantum state, unknown quantum state, and you've somehow transferred the unclonability properties into a classical serial number state, classical serial number. Okay, and so now, keeping this in mind, we can talk about a construction for this in the common reference string model. So the prover can basically generate a quantum money banknote and then provide an encryption of the witness, of the NP witness, and then provide a NIZK proof, a classical NIZK proof, that either the ciphertext is an encryption of the witness, or the CRS, the common reference string, contains the serial number that was in the quantum banknote that was sent. And then the verifier can then verify the quantum money banknote as well as the NIZK proof. And this would be the protocol. And so now just, yeah, so I will basically go into some of the details of like the proof, just so you have a sense. But the key insight is that the adversary, the end goal is basically to say that the adversary must know the witness unless they're able to forge a quantum money banknote. So now, let's just say that assume that there is an adversary that receives an honestly generated proof, and yeah, so suppose an adversary receives an honestly generated proof, which is the proof in the protocol I had discussed earlier. Then this adversary, say that they're able to, right? Assume for the sake of contradiction that they are able to actually generate two proofs to two verifiers that accept with respect to the same CRS. So in this case, then what I'll do first is I'll say that because we have this nice classical NIZK, which has two branches in the statement, I'll switch indistinguishably to the second branch. So originally in the honestly generated proof, the prover honestly gave an encryption of the witness, but now let's switch to a setting in which I no longer provide this encryption of the witness. And I instead provide an encryption of 0. So now this proof no longer contains any information about the witness. And in particular uses the second branch I said, which is that the quantum money banknote provided, this classical serial number of that banknote is in the CRS. So now that the adversary only receives no information about the witness, if this adversary we said that this adversary is somehow still able to convince two verifiers. So what this means is that either they're able to break the unforgeability of quantum money and generate two quantum money banknotes. Given one quantum money banknote, they've now generated two that have the same serial number. And this breaks the unforgeability of quantum money. Either they've done this, or the adversary must sort of know the witness already. So what this means is that, in particular, we used an encryption scheme, right? We had the adversary, we forced them to provide an encryption of the witness. So we can actually decrypt this and see that, yeah, okay, now we have a witness for this. And to get a sense of the thing is, which is that some of the details I heard about the definition is that the definition for unclonability itself, there's a few different types of definitions you can have. The weaker version is just to say that the adversary, you use the hardness of a language and say that the adversary shouldn't be able, because it was given a hard instance, the adversary shouldn't be able to come up with the witness. And so this final thing will be a contradiction to the hardness of the language. And another alternative is that we can just have a property we call unclonable extractability, which is that we can extract the witness from the adversary. And yeah, so these are some more details. You can see the proof for more specificity. The one thing I want to mention is that a question that you might have is, well, it seems that we're fundamentally relying on the properties of quantum money. And it turns out that, yes, this is true in some sense, because unclonable NISICs imply quantum money. And so in some sense, the quantum money aspect of it is sort of intrinsic to the definitions that we have provided and come up with. And so in particular, I can just say that you can see this reduction from if you have an unclonable NISIC, you can construct quantum money. And in particular, the banknote will sample some hard instances. I'm talking about this, the simplest definition of unclonable proofs, unclonable NISICs, which is you have a hard instance. And if the banknote can just, the bank can just generate a hard instance and will then perform the setup for the unclonable NISIC proof, and then provide the proof. And the proof is the quantum aspect. And then, so then the banknote becomes, the proof is the quantum state for the banknote, and the CRS and instance become the classical serial number for this banknote. And then the verifier then can use the unclonable NISIC verifier in order to verify this quantum money banknote. And yeah, and you can basically reason that, yeah, because the unclonable NISIC is unclonable and has our definition of unclonability for hard instances, this will actually end up being a quantum money banknote. So yeah, just to summarize, just to summarize, we define unclonable NISICs as well as unclonable extractable NISICs, and then we show that quantum money and other standard assumptions can be used to construct unclonable NISICs in both the CRS and quantum random oracle model. And then we also show that, well, this quantum money is inherent to unclonable NISICs, and show that unclonable NISIC implies quantum money in the CRS and quantum random oracle model. Yeah, and yeah, so I'm ending a bit early, but this is, feel free to ask questions now.
Yeah, thank you, Ruta, for your great talk. Any questions from the audience? Yeah.
Okay. Okay, yeah, okay, great question. So let's see.
Because this seems very similar to double spending attacks in general. Like you can achieve this with ring signatures, right? The anonymity property. So
yeah. So yeah, so this is, I mean, it is possible to think about this in terms of blockchain, but there's one fundamental problem, I think, in my opinion, which is that blockchain, as I understand, is basically meant to be like publicly verified and publicly accessible. So the problem with using quantum in this setting and just like blindly is that, well, a quantum proof is just like, I send it to you and creating copies will, like, I'll have to create many copies, right? There's no way I can publicly publish one quantum proof that everyone can access in a way that necessarily makes sense in terms of quantum mechanics, but it is possible. So then you'd have to move to a modified setting, right? Where like you don't publicly publish one proof, but maybe you publish some kind of way to set up this proof. And so then, yeah, and then each person would have to run the setup and receive the quantum proof, and then maybe it may not be possible. But yeah, that would be very interesting. Like unclonable signatures could potentially be useful. Yeah.
Thank you.
Other questions? Okay, I have a quick question. So can you say a bit more on how do you define non-nullability in the context of quantum proofs?
Okay. Yeah. So in particular, what we defined is more simulation extractability. And so simulation extractability in particular, the important thing is also that we're working for NP. And so there's a classical witness that's being extracted. And so like in particular, you can kind of see that like, because I sent a classical encryption of a classical witness, it is, you can define extraction as that you are able to retrieve the witness, and the extractor seems clear because it would just be a decryption for the classical encryption. Yeah. And but in the actual paper, we actually do simulation sound NIZK, like classical NIZK, and so then or simulation extractable classical NIZK, and so you use the extractor for this underlying NIZK. Yeah.
Other questions? And just one final question. So you also mentioned like that, so you have like these two relations that you need quantum money and sigma proofs to get NIZK, and NIZK implies quantum money. Do you think it would be actually possible to have like an equivalence, like to show that basically you don't even like the sigma protocols for this direction?
Oh, I see. The thing about oh, I see. So you're talking about the quantum random oracle scheme. Yeah. So yeah, so it may be possible. So as I said like kind of like quantum money and some other standard assumptions will give you unclonable NIZK. I mean, yeah, it would be a very interesting question to see if just quantum money would get you this. There's a little bit of like, yeah, you need, yeah, but in some sense, like the constructions of quantum money, one of which I think is happening after this talk, prior work had just done at the time of working on this had come from IO and post-quantum IO and one-way functions. And so like it was already kind of like assuming quantum money already gave you some kind of assumptions on other primitives that you would need. But yeah.
If there are no more questions, let's thank the speaker again. Have a great talk. Okay, so for the second talk of the session, we'll have Hart that will talk about quantum money from class group actions on elliptic curves. Yeah, the scene is yours.
Awesome. Can everybody hear me? Great. Awesome. All right, so let's get started. So I'm Hart, and today I'm going to be talking about quantum money from class group actions on elliptic curves. And this is a joint work with Shahed Sharif. So today, I'm going to start by going over some quantum money background. Then I'm going to talk about why we should care about quantum money. I'm going to explain the starting point of our scheme, which is this invariant money, quantum money construction from LMZ23. And then I'm going to get into our construction, which is just quantum lightning from Isogenies. So I think there are a lot of really interesting opportunities for future work in this area, and we'll discuss these throughout the talk. And I also apologize in advance. We are going to employ sort of a wide range of both quantum stuff and number theory stuff, and I can't give all the background for this, but I'll do my best to explain everything in detail. Right, so what is quantum money? So as you saw in the previous talk, the main idea is to use quantum no cloning and cryptography to create verifiable money in some sense that can't be duplicated. So the history of quantum money began all the way actually in 1970, really before public key cryptography got started with the secret key quantum money scheme of Wiesner. But what most people think of as quantum money today started with this public key quantum money scheme built by Scott Aronson in 2009. And the core idea here is that anyone can verify that something is a quantum money state. So for a quantum money definition, I'm going to use what's called the mini scheme paradigm from Aronson Cristiano. And they define quantum money as a tuple of algorithms, gen and verify. Gen outputs a quantum money state and a classical serial number, and verify takes these two parameters and either accepts or rejects. And Aronson and Cristiano showed that this very basic mini scheme with digital signatures implies a full scheme. So in addition to quantum money, I'm also going to talk about quantum lightning today. And these are sort of the security definitions. So a scheme is secure quantum money if no efficient adversary, when given a banknote and serial number, can create two banknotes that both verify for that particular serial number. On the other hand, in quantum lightning, an adversary can pick their own serial number and then generate two different quantum banknotes that verify under that serial number. Excuse me. Right. And this isn't exactly accurate, but I like to think of this as quantum money sort of has a classical analog of like a second preimage resistance for a hash function, and quantum lightning is analogous to collision resistance. So why should we care about quantum money? Well, I hope Ruta's talk recently, gave one good reason, but I do want to note that quantum money is extremely useful for proofs, many of which that don't, require quantum lightning or seem to use it. And I want to point out that, Mark Zandri interestingly showed an impossibility result for quantum lightning actually makes many quantum cryptographic security proofs much easier, particularly those that require rewinding or many rounds. But it's obviously much more exciting if we can actually build quantum money and quantum lightning. And as somebody asked in the last talk, quantum money can really replace blockchains for cryptocurrencies and NFTs. So quantum money has a lot of advantages over something like Bitcoin. It's fully decentralized. Typically in Bitcoin, you'd use consensus to solve double spending, but in quantum money, we use no cloning. It's also optimally scalable and perfectly private, and it breaks Vitalik Buterin's famous blockchain trilemma. And lots of people are actually interested. So this was a talk at DevConnect last year from Justin Drake, who was talking about one-shot signatures, which are an even more powerful primitive than quantum lightning, if you're familiar with them. And he referred to them as sort of, the new blockchain endgame. So a lot of people are paying attention to this topic, even if it's not going to be relevant until we sort of can all have quantum computers in our cell phones. Right. So unfortunately, quantum money is very hard to build. So here's a list of a lot of the older schemes, and you'll generally find that they're either broken, the assumptions have not been well studied, or there are no concrete constructions. A lot of very smart people like Mark Zandri, Scott Aronson, Daniel Kane, Alice Silverberg, you name it. A lot of really smart people have tried to build quantum money. But there is sort of some hope. So in the past year, we've had a few concrete constructions. At the end of last year, Mark showed a construction using group actions. Then, of course, there's this work, which I'm going to talk more detail about later. And there's a very new and very exciting construction from a classical assumption on non-abelian group actions. But again, these are not very well studied. And maybe we'll see one of your names here in this slide at the next time somebody gives a quantum money talk. So with that being said, let's get into the more technical portion of this talk. So the backbone of our scheme is this quantum lightning from walkable invariance construction from this LMZ 23 paper last year. And a walkable invariant is defined to have two sets. So we have a set X and a set Y with subsets O and two functions. We have an invariant function, which maps X to Y, and a sigma function, which permutes X to X. And the properties here are very important. We require that every element in the same O maps to the same Y value, and we require that the permutation sigmas respect the O values, or the O subsets. So if an element is in one O, it gets permuted to the same O. So really the O's kind of look like this, the under the sigmas. Right. So with this, we can sort of build a quantum lightning scheme in actually a pretty straightforward manner. The basic idea is we start by sampling a superposition of all set elements. We compute this invariant in superposition and measure the output. And then our banknote is this quantum state, and the serial number is this invariant value. So this state now is sort of a superposition of all orbits that map to Y. And those O subsets could have multiple orbits or could not, if you want to get into the algebra. Right. So for verify, we just check that the money state is well formatted and the invariant value is correct. And then we compute this approximate projection. And this is a little complicated. What this projection just says is we're projecting to the essentially honest money state, the uniform superposition over all orbits that map to Y. We can't do this exactly, but we can do it approximately. And the very rough idea that dates back to this quantum money from Knott's paper is to use these permutations to sort of randomize the superposition and then check that it's still the same. Sorry, I'm going the wrong way. Right. So you can think of it as if we have a uniform superposition over something and we permute it, it stays the same. If we have sort of a single point and we apply a permutation, then it changes completely. And we can check this using something similar to a quantum swap test. And in this older paper, we showed that if the sigma i's are sort of mixing enough, then this approximation is close enough to this sort of actual projection. So for security, we required two assumptions for this generic construction. The first was this pathfinding problem, which basically said, given two elements in the set, find a sequence of permutations between them. The classical analog of this is just like discrete log, or if you're familiar with it, group action discrete log. It's quite straightforward. The knowledge of path assumption, on the other hand, sort of states that for any algorithm that outputs two set elements, there's an extractor that outputs a path in terms of the sigmas between them. The classical analog of this is a knowledge of exponent assumption, if you're familiar with that. So the hardness of pathfinding is typically, standard or very reasonable, but the knowledge of path assumption has actually been broken. And I'll talk about this later. It hasn't been broken in a sort of useful way, though. Right. So the candidate construction from group actions that was shown in this paper is almost identical to this generic construction from walkable invariance. The key point is that we're just going to use the group action to sort of compute these sigmas, and that's just it. So I do want to point out that in this previous paper, we didn't actually show how to build an instantiable construction of quantum money because we couldn't satisfy certain requirements of the scheme. We need oblivious sampleability of the set elements, right? Remember how I talked about we were going to sample a superposition over these set elements. So this is not known for many group actions. We also need, regular group actions or sort of good group actions, and we need a new security proof. And in this work, as I'm going to get to, we solve all these problems with new results on isogenies. This does require us to get our hands dirty with math. The basic idea, which was sort of stated but not fleshed out in this LMZ paper, is our set is going to consist of elements of elliptic curves with some related structure. Our invariant is going to be the number of points on elliptic curves. Remember that isogenies only map between curves with the same number of points, and we're going to use isogenies as our permutations. And as you can see here, we have a lot of the same problems that apply. So unfortunately, we are going to have to get our hands dirty with math. I'm going to try to go through this quickly. We're going to represent elliptic curves by J invariant and twist pairs. If you're familiar with isogenies, you're probably comfortable with this. I'm going to define a couple of sampling distributions we're going to use, just the uniform distribution by sampling sort of J and B as we defined above, And if you're familiar with isogenies, there's this Weierstrass distribution. These two distributions are statistically close, but this allows us to pull in, theorems from math. Some basic elliptic curve notation. If you're familiar with elliptic curves, you already probably know this. If you don't worry about it. I'll go over everything at a high level. But what I do want to point out is on the far right of this screen, we have this squiggly E set of elliptic curves class. And what this basically means is we're having some properties of the Frobenius discriminant met that make sure our elliptic curve class has enough points and is non-degenerate. So yes, yuck, math. Do I have to? Well, no, our goal is that with the paper and the presentation, these tools are self-contained enough so that you can use them in other contexts. So no presentation is good without a picture of a nice isogeny graph. We're using considerably simpler isogenies than what you saw this morning in the squeezine talks. But here's a nice example of a representation in a kind of isogeny we'd use. Right. So let's get into fixing these problems that we had with the group action scheme by working with isogenies. So the question number one is, how can we sample superpositions of random isogeny classes, right? How we represent classes is important. Remember, we're using this J invariant twist notation. And the basic idea is pretty simple, right? So we're going to sample our J and B appropriately. Then we're going to check the Frobenius discriminant to make sure we have our nice class of elliptic curves. And if we don't get it, we're going to start over. This should already be raising some alarm flags. Maybe we have to start over too much, but we'll get into that later. It is not known how to do this for supersingular curves, so we have to use the class of all isogenies. Right. Our invariant is, again, the number of points on the curve. I'm sure most of you know that you can compute this with Schupf's algorithm. And then, therefore, our superposition sampler simply becomes, we start with the superposition over our good class. We measure the number of points in an adjacent register. We measure the contents of this register, and we get a superposition over all elliptic curves in our nice elliptic curve set in some isogeny class. And I do want to point out that we can target a random isogeny class this way, but not a specific one. And that's sort of why our quantum money and quantum lightning scheme is secure. So there's this problem. We need to be able to sample uniform superpositions over large isogeny classes. It turns out, and I didn't know this before we really started this work, that we didn't even know how large isogeny classes are over a fixed FP on average. So we actually show this. And so this theorem, which is a lot of math, basically says that if we sample a random elliptic curve from one of these distributions, then with probability actually 14%, we get a non-degenerate class of curves, and it has a large isogeny class. So we get a lot of different elliptic curves in the class. And this means we can obliviously sample elliptic curves over FP that have large class groups. And previous work, even in the pure math space, restricted to either isogeny classes of supersingular curves or light on heuristics. So the best result we had before was an asymptotic result. So it turns out, with all of these, random elliptic curves, we need to make sure they're group actions. We need to be able to compute on them. And so to do this, we use this nice theorem from this DKS 18 paper. Luca's in the audience back here. He can tell you more about this than I can, obviously. But what this theorem basically says is that we can efficiently compute isogenies in these random isogeny classes we can sample. I will say efficiently is polynomial time. This is not concrete efficiently, but it is what it is. If you're familiar with the notion of Elke steps, that's what's going on here. Okay, and there's another gotcha in this. Well, what about prime ideals? We need to be able to generate these prime ideals from this isogeny class. And it turns out we can using this idea of a Bach generating set. So the Bach generating sets, assuming the generalized Riemann hypothesis, do in fact generate the class group. And sort of an abbreviated theorem is that there is an efficient classical algorithm to generate this list of prime ideals. So this sort of means we can create a generating set that lets us compute all these possible isogenies. You can think of this as sort of analogous to sampling generators for a group. so you can generate the whole group. And then the final question you might ask, well, not the final question, but a question is, are we mixing fast enough using this Bach generating set, right? As the theorem in the paper says, it's only if these sort of sigma i's are mixing enough, then this, permute and then check if the state is the same actually works. So you could imagine, right, trying to generate the whole group of integers under addition for some large prime, using just group operations and small generators like 1, 2, 3, right? It would take you an exponential number of steps to wrap around mod p just using addition. So, how do we fix this? Well, unfortunately, we have to make an assumption here. So we say that a sequence of elements in G is weakly Erdős-Rényi if for every element in G, we can write G as a subset product of this sequence of elements. And we define this thing we call the Bach Erdős-Rényi game, which basically says an adversary can win if it can find an imaginary quadratic field with some discriminant big enough such that these Bach generating sets are not weakly Erdős-Rényi. We believe this is hard. We justify this assumption in the paper. It's known to be true for randomly chosen sequences in abelian groups. We argue in the paper why we think BK behaves sufficiently randomly. And then with this in mind, we can have this like complicated and nasty looking theorem, which uses the isogeny graph. If you're familiar with isogenies, you've probably seen something like this before. If not, well, what this basically means is it means that, if this Erdős-Rényi assumption holds, then the isogeny graph is essentially an expander, and we don't have to do too much computation to sort of randomize an elliptic curve over an isogeny classes. In other words, our isogeny classes are sort of mixing enough to meet the template of an invariant money scheme. And the right analogy is, again, expander curves. So right, that's it. That's our, we can sort of use these facts to build a construction. Our superposition is the set of all curves and this nice, with these nice properties. Our invariance is, again, the number of points. So we compute the number of points using Schuf's algorithm. We measure that. And then our state is this quantum superposition, and our serial number is the number of points. To verify, we just check that everything is properly formatted. The number of points is n. And we compute the approximate projection value measured that we described earlier, apply it to the state, and we accept if the measurement passes. The main difference from before is that in this case, we only have a single orbit for each honest money state. So we can use a slightly different proof than the invariant money scheme. And finally, what about security, right? I told you the invariant money security proof was broken. What can we do about a proof? So it turns out the basic security of our scheme follows from a very simple, although ad hoc assumption. So if there is no efficient adversary that can create two uniform superpositions over an isogeny class in this nice set of elliptic curves, then our quantum lightning scheme is secure. And I really like this because it means we have a very simple and seemingly fundamental quantum assumption for quantum money. That being said, definitely encourage you all to try to break it. It's a new assumption. But if you do want a generic proof, we can do that too. And if we go back to the structure of the invariant money problem or scheme, right? The hardest of pathfinding in this case is just sort of the problem of finding an isogeny between two isogenous curves. We'll call this a standard assumption. And then the knowledge of path assumption boils down to the fact that if a quantum adversary creates two elliptic curves in an isogeny class and this nice set, then it must be able to extract an isogeny between them from the adversary. Again, there's a counterexample, but the only really counterexample we know uses sampling from the Fourier domain. And it generates random elliptic curves without a path in an isogeny class. So not really useful things. We can break this, but not in a useful way. So if we want to do a generic proof, what we can do is we can use this new knowledge of path assumption, which sort of says that if there exists an adversary that wins some game or does something, and we have a formal definition of what this means in the paper, while creating two elliptic curves in an isogeny class in this nice set, in a way that it is not possible to extract an isogeny, well, there also has to exist an adversary that solves the same problem with some good probability of success that does not do this or violate this property. So we'll say, Mark uses a similar fix, or at least a similar style of fix in his earlier paper. But the assumption is a little more complicated because he needs to work in the Fourier domain. There are no known counterexamples to this at this point, but this is an excellent problem for you to work on to try to see if this sort of knowledge of path assumption is true in this weaker state. And I'll say that the security proof in our paper follows in a similar way with these modifications. And that's it. Happy to answer any questions.
Thank you, Hart, for your great talk. Any questions from the audience?
I'm sure everybody perfectly understands number theory and quantum now.
So I had a question about like the hardness of like pathfinding. So you're
Yes.
saying that's more like a standard assumption by relating to like one of these problems on isogenies.
Yeah.
I see. And about like the second assumption, I didn't quite, so that was like some knowledge of path assumption. Is that also related to like some problem on isogenies or?
Yeah, so we can define them in either a general form or sort of a form for isogenies. In the walkable invariant paper, we define them in a general form. In this paper, we define them specifically for isogenies. And the hardness of pathfinding, I put standard star. It's not completely standard because we're basically giving the adversary a choice of which isogeny class they solve this problem on. So it's sort of like, classically you could think of a discrete log problem, but I let you choose the group that you want to solve the discrete log problem on, obviously restricted to some class of groups that I consider hard. So sort of standard-ish, probably standard, but you can't reduce it back to a single group, obviously. Pathfinding is much more complicated. The state of this feels relatively unsatisfactory at this point. That being said, if you can break this assumption and do something useful, like a useful break, it would be, sort of a breakthrough in the quantum area of sort of the power of forgetting, right? You could really show that we could do more things quantumly by forgetting stuff. And that would be kind of a cool theoretical result. So sorry for the long-winded answer.
Thanks. Other questions?
I'm happy to take questions offline. But go give Luca the hard isogeny questions, please.
I just had like one final question. So for the verification where you're seeing that you wanted to verify like the number of points is equal to n.
Mhm.
So what happens if you have something closer, let's say like n-1 points? What happens?
You reject it.
I see.
So it has to be exactly n.
Makes sense. Thank you. Okay, if there are no other questions, let's thank Hart again for his great talk.
Thanks a lot.
But okay, so for the final talk of the session, we'll have Jinwei talk about adaptive hardcore bit and quantum key leasing over classical channels from LW with polynomial modulus.
Okay,
The stage is yours.
can you hear me?
Oui.
Okay. Thanks for Cojocaru's introduction. And today I will present our work about adaptive hardcore bit and quantum key leasing over classical channel from LW with polynomial modulus. Okay, it's a long title. And this is a joint work with Donghui Fan, Wei Changwen, Xin Yuyan. So first, let's see what is proof of contentness. A proof of contentness is a protocol between two parties, and the prover want to show that he has the quantum resource. And here are some schemes of proof of contentness that based on LW. And then what is secure key leasing? Secure key leasing is it means when someone get into a company or organization, he will be given a key, and when he leaves, the key will be revoked. Here are some solutions to the secure key leasing. either on the quantum channel or the classical channel. And our result, let's show our result. And as to the proof of quantumness, the previous work either rely on LW over the superpolynomial or the LW, but with some additional assumptions. But our works only rely on the LW over the polynomial modulus. And as to the public key encryption with the secret key leasing, over the classical channel, the previous one rely on the is on the superpolynomial modulus, but ours are on the polynomial modulus. Okay, this is the roadmap, and let's start with from the proof of quantumness. Okay, in order to introduce the proof of quantumness, we need to start with the concept of cloud-free function. A cloud-free function is a pair of public injective function f0 and f1 with the same range, and it has the following two essential properties. It means first, if we give for any y in the range, it has two pre-image, and these two pre-image is the cloud. And additionally, the cloud-free means for any y in the range, the cloud is hard to find. Okay, then we move to a LW-based cloud-free function. So if you are given a LW sample, can you get a cloud-free function? And here is the candidate, but we say that if we have the AX and we can compute X easily, so it's not cloud-free. And let's say the evaluation of fk0 on the X and the evaluation of fk1 on the X minus S. And we found that although it's not equal, but it's very close. So Brzezinski et al. 18 give a solution to this problem. Instead of using the exact function, they use the distribution function like this. And we found that the support set of these two distribution function has large intersection and for any y in this intersection, it has a cloud, and the cloud is X at X minus S. And then cloud-free here, if we given y and find the cloud X and X minus S, it means that we can compute S easily. Otherwise, and then we can break the LW, which is very hard. So let's see how to generate a cloud in a superposition. First, we use GR02 result to generate this quantum state, and then we try to compute like this, given a LW sample, and after we measure the last register, we will get the value of the measurement like y equals ax plus e prime, and this y follow the distribution of either of these two distribution fk0x or fk1x minus s. And when this ratio is E0 over E is negligible, y for in this the intersection overwhelmingly, and we can after we measure the last register, we can get a quantum state cloud superposition like 0x plus 1x minus s. And to be simplified, we use the notation below. And if we have this quantum state, have the cloud superposition, we can do the standard measurement, and then we can get either of these two superposition, or we can do the Hadamard measurement, and we will get a pair CD. And Brzezinski et al. 18 show that the D here is a random vector, and C satisfies this equation, and it can be reformalized as the adaptive Huggle bit. So a very natural question is, can we get both value of the measurement? the answer is no. And Barkowski et al. 18 show that on the assumption of LWE with a super polynomial modular, it's hard to get the adaptive Huggle bit. It's a C here. And in other words, it's hard to get B, X, B, C, and D at the same time. So it's hard to get both value of the measurement. And then let's move to the proof of quantumness. If we ask randomly for the value on the either Hadamard measurement or the standard measurement, let's see the behavior of the quantum computer. The quantum computer can move between Hadamard basis and standard basis, so he can reply accordingly, and this guarantees the completeness. And but if we only have the classical computer, and we want to pass the test, we have to prepare both value of the measurement. So, but it's very hard because of the adaptive Huggle bit. This guarantees the soundness. Okay, to be more precise, after we given that LW sample, we can generate the cloud superposition and get a measurement as value of a measurement y here. And as we said before, we can use it to prove the quantumness. Okay, but the previous schemes rely on the super polynomial modular. But can we get a proof of quantumness based on the LW over the polynomial modulars? We separate it into. We need to consider two problems. Can we guarantee the soundness, and can we guarantee the completeness? First, we consider soundness. And if we want to guarantee the soundness, we need to have adaptive Huggle bit with polynomial modular. And now let's first sketch the proof of adaptive Huggle bit in the Barkowski et al. 18. And their target is to cover the information of S as much as possible. And then so they use the Spalding noise E0 here to cover the whole information of Fs, and then they prove that on the condition that CS is fixed, and then the inner product is a random bit, and then they prove that adaptive Huggle bit. But is it necessary to cover it? Actually not. And inspired by Barkowski and Dontling's 820s, we separated the E0 to two parts, FE01 plus E02. And we want to use the E01 to cover the information of S. But we say, of course, we also don't need to completely cover the information of S with the E01. And we point out that when the Ys of the E01 is about N, and on the condition that CS and S E01 are fixed, this is also a random bit. That's then we get an adaptive Huggle bit with polynomial modular, and then it can guarantee the soundness. How about the completeness? Or to be more precise, if this ratio E0 over E is noticeable, Barkowski et al. 20 has considered this problem. They show that they show that in this ratio, if the ratio is noticeable, we will generate a cloud superposition, not uniform anymore. And when we do the Hadamard measurement, we'll get a pair CD, but the Hadamard equation can be only satisfied with the probability at least 0.8. So after proper parameter setting, so can the quantum computer pass a trick? If it do the standard measurement, and we can still get either of these two possibility. But if we do the Hadamard measurement, since the probability is at least 0.8, so we just need to set a threshold 0.75. And for the honest prover, he can pass the trick overwhelmingly. But for malicious prover who can only pass each test for with a probability about 0.5, and it is below the threshold, and he cannot pass the test. So we guarantee the completeness, and then we get a proof of quantumness based on LW or polynomial modulus. And then let's go to the second part. It's about the public key encryption with secret key leasing. And yes, this is previously the shadow valise 23 gave a very brilliant framework of it, and it means that even after given the master public key, the lazy will generate a public key and a secret key, and the lazy can use the secret key to decrypt it. And after required, the lazy can delete the secret key. Okay, let's see how shadow valise 23 generates the secret key and a public key. They just do the same thing. They after get the doubly sample, and then they generate the cloud superposition and get a evaluation like y like this in this form, and like the master let the public key as BA, BY, and let the cloud superposition as a cloud superposition. Let the secret key as a cloud superposition, and if we move it to the modular to the polynomial modular, the only change here is the secret key is no longer a uniform secret, and the secret key is no longer a uniform cloud superposition, but yes, as we mentioned before. So let's see how to encrypt and decrypt. This is also according to the shadow valise 23 framework, and we can encrypt like this. And when we want to decrypt, and then we can decrypt in this process, and we can notice that either of these two possibility of the cloud superposition can be considered as a secret key, and they can decrypt the separate text, and then finally we can generate a register store the information of the message. So after we measure this register, and it doesn't influence the cloud superposition, so we can reuse the secret key. So as to the in the CPA security, it means that we need to guarantee we need to prove that the encryption of 0 and encryption of 1 is indistinguishable, and the main issue exists in the third component. Or in the other word, we need to prove that this part R transport AX plus R transport E plus E prime is indistinguishable with a uniform random. So the shadow valise 23 show that we only need to prove that R transport A is a uniform random over the ZQN on the condition that R transport E. So in their paper, in order here we cannot use the universal hash here, because Y is given by the adversary, and so E is also given by the adversary, and so we cannot guarantee that E don't have any relationship with the A, so we cannot use the universal hash here. So in order to cover the second part, they use the noise flooding again to cover the whole part of R transport E, and the flooding noise is E prime, and then they use the leftover hash lemma on the first component, and then they prove that the first component is uniform random. But we say it's not necessary to use the uniform random. It's to use the noise flooding. Instead of using the flooding noise, we use the R transport E instead, and actually we want to use the E1 to get the value of E, and we denote the E minus E1 as E1 prime, and we denote the 0 place as Z, and we can find that the corresponding RZ in the second part has been completely hidden, and the information of the RZ can only exist in the first component. So we can use the lambda hash lemma on the first component, and then we can prove that the first component is uniform random of the ZQN. So at last, let's see how to delete. In the shadow list 23, they show that if we want to delete the secret key, we only need to do the Hadamard measurement, and then we can get a pair CD. And because due to the adaptive Hago bit, if we get the CD, we cannot get either of these two possibility in the class superposition. So we lose the ability to decrypt. And then the laser just need to check if the Hadamard equation is satisfied. But if we move to the polynomial modular, let's see what happened. First, the secret key is not a uniform class superposition as we said before. So the Hadamard equation cannot always be satisfied. It can only be satisfied with a probability at least 0.8. So as we can use the previous method and set a threshold 0.75, and for honest lazy, he can always pass a check. But for malicious lazy, he can only pass each test with a probability about 0.5, but it's hard for them to pass the check. So how about the further work? We can focus on two things. For example, the application of the gnosis for NTCF, and for example, the efficient revocable quantum digital signature based on gnosis for NTCF, or the quantum delegated computation based on NTCF. Or we can consider about the application of the secure key leasing, for example, revocable broadcast encryption, something other or interesting things. Okay, so it's a reference, and any question?
Thank you, Jinwei, for a great talk. Any questions from the audience?
Its complete paper is not available on the conference page.
Which?
Sorry?
This paper and presentation is not available on the conference page. So just want to know how can we get it?
You mean like how we can find the paper for this talk? I think probably the authors can tell you offline how to get the link to the paper. Any other questions? Okay, so I was curious. So, do I understand correctly that basically, the two improvements you get to allow for LW with polynomial modulus are essentially because you are able to construct this TCF, these trapdoor-Crofty functions, you adapt a hardcore bit from just LW modulus. That's where the advantage comes from. So essentially, for both applications, you have the same construction, but you are able to show how to construct these underlying families from polynomial modulus.
Yeah,
I see. And is the hardness due to the adaptive hardcore bit, or is just or is even from claw free? It's already hard to show how to construct it.
I think the hardness is adaptive hardcore bit.
Sorry?
I think the most hard part is adaptive Jacobi. The most important part is adaptive Jacobi.
I see. Okay.
Adaptive Jacobi over the polynomial modulus. Yes, because the previous one is based on the super polynomial modulus, and now we give it adaptive Jacobi on the polynomial modulus, and it can be used in many situations. Yeah.
Right. And so my second question is like in the context of like proof of quantumness, like the second work you were mentioning, like the BKEVV, is that also relying on the adaptive hardcore bit? Because I thought they were just assuming TCF.
They don't use the adaptive Jacobi. They only they use yes, they also there's one sorry. Here. Okay. Here.
Yes.
Yes. Yes. They use the polynomial modular, but in order to avoid the adaptive Jacobi, they use the random oracle instead. So in that paper, they don't use adaptive. So yes, that's why they can use the polynomial modular.
Okay, great. Great. Thank you. Other questions from the audience? Okay, if not, let's thank the speaker and all the speakers of the session.